Hello everyone. Today I want to talk about what I'll call the silverware factory. So this is kind of an application of linear algebra in a somewhat artificial setting, but I just wanted to show you guys how these ideas of echelon, reduced echelon solution sets, how this might actually have applications in the quote unquote real world. So here's my setup. So we make silverware at the costs of, let's say, forks, which let's say are $5, spoons, which are $3, and knives, which are $2. I have no idea how much these actually cost, but let's just pick these numbers. For some reason, forks are very expensive these days. Okay, so here's our goal. So we're in this factory. Our goal is, maybe our boss tells us that we want to satisfy various things. We want to satisfy, so let me say, the first thing I want to satisfy is I want to spend $1,000 on production. The second thing I want to satisfy, that I've been told to satisfy, is I want to make a total of 100 pieces, let's say. Okay? And then the last thing is that the number of forks should equal, say, the number of spoons produced. Okay, so for some reason we know that the restaurants always want the same number of forks and spoons, so we want to produce the same number. Okay, and so then the question is, can we do it? And if so, how? Right, so you should realize that these questions are very similar to kind of, the first questions we ask with any system is it consistent? If so, what is the solution set? So that should kind of look familiar. So here's how we do it. We're going to use linear algebra. What I'm going to first do is set up some notation. Let's say F be the number of forks produced. S will be the number of spoons produced. And K will be the number of knives produced. And so now I want to realize that these three conditions are actually linear equations. So for instance, one becomes, well, how do I know that I spent $1,000? Well, every fork costs $5, I want 5F. Every spoon costs $3, I want 3S. Every knife costs $2, so this will be 2K. And this should equal 1,000, right? What about equation 2? A total of 100 pieces. Well, remember the F was the number of forks, S was the number of spoons, K was the number of knives. So I just want the sum of these things to be 100, right? And then finally, what does it mean to say the number of forks equals the number of spoons? Well, we know that's F equals S, but I want to write that as something with the variables equals a number. So I'm going to write that as F minus S equals 0. Okay, what is this? This is a 3 by 3 system, right? 3 equations and 3 variables. Okay, cool. So that's what we know and love, right? That's the business we're in, is to solve such systems. So how do you do this? So as usual, we solve this guy via the augmented matrix, by reducing the augmented matrix. So let me say reducing the augmented matrix. And let's see, can I fit this in the screen? So I want to know, what is the augmented matrix? Well, it's 5, 3, 2 augmented with 1,000, 1, 1, 1 augmented with 100, 1 minus 1, 0 augmented with 0. Right, that's the system. That's the same information. And let me spare you the details here, but you guys know how to row reduce this guy. It turns out that what you get is this. 200, 200, minus 300. So what this is saying is that this is a consistent system, right? You've got pivots in every row. There's no 0, 0, 0 bad thing. So this is mathematically a consistent system. And it has a unique solution, right? There's no free variables. The unique solution is, well, 200, 200, minus 300. Now, wait a second, right? This is the number of forks, this is the number of spoons, this is the number of knives. So if you go to your boss and say, oh yeah, we can do this, but the number of knives, you just need to make minus 300 of them. So this is a case where, you have the mathematics working for you, but you have to interpret things. So, when you're actually trying to apply this to a model, you want to know, is this actually feasible for your model? And not so much, right? But, you can't make minus 300 things. So there are ways to fix that actually in the math that we're not really going to talk about. But what I want to, again, I just want you to realize that this is a consistent system. It gives you a unique solution, but it's not really, feasible. So in some sense, you can't do it in the real world. But mathematically, it's fine. Let me go back and switch things. So what we're seeing is that, if we want to actually have a realistic solution, it ain't going to happen. Let me see if I have a color here. I'm going to change my setup. So instead of 100, I'm going to have 400 pieces. Okay. So of course, this changes this to 400. And now, how does the system change? So I'm now looking at, let's see if I can fit this on the page. Well, you guys can remember this. So the new system is what? It's going to be 5, 3, 2, 1,000. 1, 1, 1, now 400, because I'm going to make 400 things. And I still have this forks equals spoons thing. And this reduces to, well, of course, the coefficient matrix reduces to the same thing. It turns out now this will be 50, 50, 300, if I did it correctly. Okay, that looks good. It's another consistent system with unique solution. So again, unique solution. And what is it? Well, 50, 50, 50, 50, 50, 300. So notice, of course, that the forks equals the spoons. That's what we imposed on the system. And it turns out this is the one and only one way, the one and only one way to do this. Let me show you guys a couple other things I can do. So let's see. So going back, so again, this is a case where you have a unique solution. What if you go back to this setup, and suppose I only, well, suppose I add another restriction. So let me do it this way. So now suppose the boss says, okay, yeah, that's good, you can do that, but I also wanted the number of forks to be the number of knives. We want the number of forks to be equal to the number of knives. So this adds a new equation. Maybe I'll call it 4. So if I go back to my, my system here, this is the equations that I'm working with. This is going to add a new one. We want f minus k equals 0. And so what's the system now? Well, right, it's the same as before. We still have the 5, 3, 2, 1,000. We still have the 1, 1, 1, 400, right? We still have the 1 minus 1, 0, 0, because that's the forks equals the number of spoons. But now we're adding forks equals 9, so f minus k equals 0. And what this reduces to is the following. So let me just do it here. So this will actually reduce to the following. So you'll have, well, you're going to have something 1, 0, 0, 0, 1, 0. I don't really care. It's 0, 0, 1. But what's going to happen now is you have 0, 0, 0, and this will be, well, I forgot what it is, but it's some non-zero number. So you'll have something like 50 here, right? And so what is that telling you? It's telling you you've got this, this bad row. So that's bad news, right? Because you've got, well, it's an inconsistent system, right? So this is now inconsistent. No solution exists. So even mathematically, there's no way to do this. You can now, go to your boss and say, nope, we can't do this. There's no, I could prove this to you that there's no way to actually produce forks, knives, and spoons that satisfies the 4 equations. Okay, last thing I want to do. So last. Now let's suppose you only needed to satisfy, say, the first 2 things. So go back up here. So let's suppose you only want to satisfy the first 2 conditions. So we say, okay, never mind. I don't care that the number of forks equals the number of spoons, or the forks, the number of forks equals the number of knives. The restaurants haven't told us how they use them, so we We just want to produce this, total of $1,000 worth of merchandise, and we want to make 400 pieces. Okay, what does that look like? Well, now the system is, is 2 by 3 because I have a 5, 3, 2, 1,000, and just a 1, 1, 1, 400. And that's it, right? So I should have set up here, right, the system was, this is this overdetermined system where it's 4 by 3. This system is now underdetermined as 2 by 3. Let me press my magic row reduction. What I get here is 1, 0, minus a half augmented with minus 100. This is 0, 1, 3 halves augmented with 500, if I did it right. Okay, so what do you see here? By the way, let me just comment that we knew that this would be a consistent system because, right, if I go back to this system here, right, so this system that we looked at earlier, which was 5, 3, 2, 1, 1, 1, 1, minus 1, this was the same, this was a system that had the same conditions plus an extra equation, and it had a solution. So if this guy has a solution, then it'll, in particular, be a solution to this system where I have fewer equations to satisfy, right? If I can satisfy 2 of the equations, if I can satisfy 3 equations, then I can satisfy just 2 of them. So we know that this is consistent, but what we notice in this case is that this is not only a consistent system, it actually has infinitely many solutions, right? Infinitely many solutions because we have the third variable, which I guess was knives, right, is now free. So what's the solution set? Well, let's do it in our notation here. So forks, spoons, knives equals, well, it looks like knives is free, so we just put K. Spoons will be 500 minus 3 halves of knives. And then the number of forks will be minus 100 plus 1 half knives. Right, so I'm just using these to solve for the pivot variables. And what is this? This is minus 100, 500, 0 plus K times 1 half minus 3 halves, 1. And so, okay, you now have a kind of geometric description of all possible forks, knives, spoons that satisfy this, or forks, spoons, knives, I guess. So for instance, you can tell your boss now that he or she can pick the number of knives they want. So, you could take, I don't know, knives to be, let's say like 400, I guess would be, if K equals 400, so let's say the boss decides 400 knives should be made, then that means that the number of forks should be, well, it's minus 100 plus 200, which is 100. The number of spoons is given by 500 minus 3 halves, so that's, oh, that's not good, right? That's minus 600. So, yeah, maybe 400 would not be a good choice. Let me change this to something like, I don't know, how about 300? Because now this would be minus 100 plus 150, so this would give you 50. So we say, sorry, you can't make 400, but you can make 300. Now the number of spoons would be, what is this, minus 450. So you also get 50. Actually, that looks familiar, right? That was the solution we had before. That was actually, that's the case when forks equals spoons. But you can see how you can actually cook up all other solutions as well. Okay, so just kind of a baby example of how linear algebra can be used in production situations, things like this. And you can hopefully imagine that this can be generalized to much more sophisticated models where you have many working parts and many equations, many restrictions or equations you want to satisfy. Okay, we'll see you next time.